Hello, today's lesson is on chemical batteries, specifically something called galvanic cells. And hopefully you remember this from class. We put a whole bunch of different metals into a solution of copper 2 chloride and looked to see which metals were the most reactive. And from this, we made a reactivity list of metals. Now you may note that this is not from class because one of the metals here is lead and we didn't use lead. But I found this online and the people did a similar experiment to us, and they used different metals and they put it in a solution of copper 2 sulfate with a little bit of salt. So our reaction found out that zinc was in fact more reactive than copper, which means you can put some zinc solid into a solution of copper 2 sulfate, and zinc, since it is more reactive, this reaction will take place and zinc will steal copper's date, and we'll get copper solid and zinc 2 sulfate. And this is called a molecular equation. We also learned earlier in this unit that you can write a total ionic equation, which means that if you have an ionic compound that is aqueous, it doesn't stay together, it splits apart into the cation, copper 2 plus, and the anion, sulfate 2 minus. We took this even farther to something called a net ionic equation. For that, we noticed that sulfate 2 minus was the same on both sides. Oops, this really should say aqueous. And so we canceled that out and we were left with this net ionic equation. Zinc solid reacted with the copper 2 ions to form copper solid and zinc 2 plus. We also learned right before break that we could write this as half reactions. We could look at just what happened to the zinc and then what happened just to the copper. So let's look at this. Zinc on this side started off as a solid, and then on this side it became zinc 2 plus ions. So how did zinc solid become zinc 2 plus? What happened was that it lost 2 electrons. And then we noticed that we could get the voltage of this half reaction if we used Appendix A11. So pause the video and go to your problem book and get out page A11 and then come back and start the video again. I'll wait for you. So I have a portion of page A11 here also. And we can find, this is just the right side of page A11, that reaction of zinc 2 plus and 2 electrons going to zinc, and we get a voltage here of negative 0.76. But maybe you might remember from the previous page, so let's go back, that the reaction was written in reverse. The zinc was on the left side. So we're going to turn it around. And when we do that, we're also going to change the sign of the voltage. So from Appendix A11, we find this reaction, but it's written in reverse. So we reverse it, and we change the voltage to positive 7.76 volts. And this is oxidation, because remember the phrase we learned, Leo the lion goes grrr. So Leo, losing electrons, is oxidation. So zinc is becoming oxidized, which means copper must become reduced. So here's the half reaction for the copper. Copper 2 plus is going to copper solid. How does it do that? By taking 2 electrons. Where does it get the 2 electrons? From zinc. Zinc is more reactive, and because it's a metal, it reacts by losing electrons. So zinc, since it's more reactive, is the one that loses the electrons, and copper, since it's not as reactive, is the one that will gain electrons. So zinc is being oxidized and copper 2 plus is being reduced. And go back and look again at Appendix A11 and you can find the copper. So the copper is right here near the top of this, and we see it's written in the right order, copper 2 plus 2 electrons going to copper solid, and it has a voltage of 0.34. So let's go back here, and we see this reaction, and we put the voltage of 0.34. So what about when I put zinc with copper? I can add these two half reactions together. I get zinc plus copper 2 plus going to copper solid plus zinc 2 plus. And you notice this is way back. We had this in the net ionic equation. We just added these two half reactions together Notice the 2 electrons is on the left side and 2 electrons is on the right side, so they would cancel out, and the 2 half reactions add up to be the net ionic equation. And if I want to determine the voltage of this battery, I would add these 2 voltage together and I would get 1.10 volts. And that's if I am undergoing standard conditions, which assumes a 1 molar, which is 1 mole of ions, in this case, per liter of solution, 1 molar copper 2 plus and 1 molar zinc 2 plus. So we also drew on the board what would happen to have this galvanic cell. Now, the only way you can get a battery, you want to make the electrons go from the zinc to the copper, but you want them to go through a wire so we can use this electrons moving to create electricity. So to do this, I have to separate the zinc from the copper 2 plus solution. If I put them together, the zinc, like we did in that first reaction, that reactivity list, if I put the zinc directly in the copper 2 plus solution, there's going to be a chemical reaction, and zinc will pass its electrons right on its surface, and copper 2 plus will take the electrons and become copper solid. But then the electrons will not pass through a wire, and then I'm not going to be able to use them to run a battery, to run an electrical device or use the moving electrons as electricity. So this is a galvanic cell when you take a spontaneous redox reaction and you separate the 2 sides so that the electrons get transferred, but they have to go through a wire to get to the other side. So on this side, I would have zinc, piece of zinc metal, and instead of being in touch with the copper 2 sulfate, I put in a solution of zinc ions. And on the other side, the copper 2 plus solution I put it with copper metal, and then I connect the 2 metals with a wire where the electrons can flow through this metallic wire. And then I could connect this to some voltage meter or to some clock or something, or light bulb, and I could use the electron flow to run a device. So now the electrons, since zinc is more reactive, zinc wants to lose its electrons more than copper. So zinc will lose its electrons, and the electrons will go through this wire out to this side. And now the copper ions will take the electrons that are sitting on the copper metal and become solid copper. So this copper metal is going to get bigger and bigger because the copper is going to come out of solution and be deposited on this piece of copper. Whereas this side, the zinc is going to lose its electrons going this way, and the zinc is going to go into solution, so this electrode is going to get smaller and smaller and smaller. To complete this circuit, I have to have a complete circuit, and I add a salt bridge so that we don't end up with a buildup of positive zinc ions on this side and a depletion of positive because I'm losing copper 2 plus ions on this side. So the zinc ions will flow this way through the salt bridge, and the sulfate ions will flow this way to keep everything neutral. And then I will have a battery, and I can use it to conduct electricity. We also note some other terms. This is the anode, because anode is where the oxidation occurs. Oxidation is where the side that is losing electrons. So on the zinc side, reduction is where the cathode is, and reduction is when we gain electrons and copper is gaining electrons. So here is a picture of a galvanic cell using zinc metal and copper 2 plus ions. So here's the half reaction on the zinc side, here's the half reaction on the copper side, and if you add these 2 voltage together and put in a voltmeter, you should get a voltage of 1.10 volts. So what about balancing and adding half reactions? Well, we did a very simple example because copper was 2 plus and zinc was 2 plus. So if you notice, the balance equation all had 1s in front of it. But what if it becomes a little bit more difficult? Let's work with one of those. So instead of using zinc and copper 2 plus ions, let's do lead 2 plus ions and aluminum solid. So here we have the equation. Aluminum is more reactive, so it will react with lead 2+ and become aluminum +3 and lead solid. Let's look at the half reactions. So look at Appendix A11, and we have lead 2+ here going to lead solid. How did it go from lead 2+ to lead solid? It had to gain 2 electrons. So it has to gain 2 electrons. Let's look at the aluminum. Aluminum goes from aluminum solid to aluminum +3. And how does it do that? It has to lose 3 electrons. So what if I want to balance this reaction? You may say, but Miss Backus, this top reaction is already balanced. I have 1 lead on this side and 1 lead on the other side. I have 1 aluminum on this side and 1 aluminum on that side. So you might think it's balanced because we hadn't really talked about the charges. The charges also have to balance. I have 2+ on this side and I have a 3+ on this side. That does not balance. So how do I balance these two reactions and get the proper voltage? Well, first we get the voltage from Appendix A11. So I read this off the chart and I get a -0.13. For this one, I had to reverse it because it was written the opposite way. So instead of being -1.66 volts, it becomes a +1.66 volts. So what about these two half reactions? I'm going to have to add them together to get my net total ionic equation. But how do I do that? Well, let's think about it. If lead needs to lose 2 electrons, gain 2 electrons, and aluminum needs to lose 3 electrons, well, the only way lead can gain 2 is if it gets it from something, and the only way aluminum can lose 3 if it gets it from something. So how does this lose 2 and this gain 2 and this lose 3? Well, it doesn't. So once again, we need to think of the least common multiple of 2 and 3. So what if they have 6 electrons gained back and forth? So let's try that. So let's multiply this equation by 3. So I get 3 leads plus 6 electrons will give me 3 lead solids. And notice I'm not going to multiply this voltage by 3. That's kind of odd. But it's the potential difference between the lead ions and the aluminum and is the same voltage regardless of how many I take. And then if I want 6 electrons lost, I multiply this equation by 2. I get 2 aluminums going to 2 aluminums plus 6 electrons. Now I can add these two equations together. I have 2 aluminum solids plus 3 lead 2+ plus 6 electrons gives me 3 lead solids plus 2 aluminum plus 6 electrons. And hopefully you can see that there will be 6 electrons on both sides, so we can get rid of that. And here's my net ionic equation. 3 lead ions plus 2 aluminum solids gives 3 lead solids and 2 aluminums. And now I add these two voltages together. So this battery would have a voltage of 1.53 volts. So there you have it, a little introduction to galvanic cells. Hope you enjoyed listening. I enjoyed sharing it with you. See you in class.